Good day, everyone. So today we shall be looking at questions and answers on energy quantization. All right, let's dive into this. Okay, example one says an electron makes a transition from a certain energy level EK to the ground state E0. If the frequency of emission is 8.0 times 10 to the power 14 Hz, the energy emitted is what? Take Planck constant, which is h, to be equal to 6.6 times 10 to the power minus 34 jouleseconds. Good. So what we need to do here is to write out our parameters first. So one of the parameters given to us here is the Planck constant, that's the h. So it's written out 6.6 times 10 to the power minus 34 jouleseconds. And then we are also given the frequency of the emission, which is 8.0 times 10 to the power 14 Hz. Then we are made to calculate the energy, okay? The energy emitted, okay? That's our capital E unknown. By formula, the energy emitted is the product of Planck constant and frequency. The Planck constant is h multiplied by the frequency, which is f. So 6.6 times 10 to the power minus 34, that is the Planck constant multiplied by the frequency, is 8.0 times 10 to the power 14. And when you do this, the result will be 5.28 times 10 to the power minus 19 joule. Alright, so that's the energy emitted when there is a transition of the electron from EK to E0. Okay, so let's take another example. Here it says, calculate the energy carried by an X-ray of wavelength 6.0 times 10 with power minus 10 meters. Taking Planck constant, that is our h, to be 6.6 times 10 to the power minus 34 jouleseconds. Then velocity of light to be 3.0 times 10 to the power 8 meter per second. Okay, so we have to look for the energy, that's our capital E unknown, and then we are given the other parameters. So we are given the wavelength, that is lambda, to be 6.0 times 10 to the power minus 10 meter, that's our lambda. So our lambda is equal to that value. And then our Planck constant, which is h, is thus 6.6 times 10 to the power minus 34 jouleseconds. It's given the question already. Velocity of light usually is represented with letter c, so our c is equal to 3.0 times 10 to the power 8 meter per second. To determine our energy, in this case, our energy will be equal to the product of Planck constant and speed of light, or velocity of light, all over the lambda, which is the wavelength. Okay, so AC over lambda. Now our h is given to be 6.6 times 10 to the power 34. Our c, which is the speed of light, is 3.0 times 10 to the power 8. Of course, the lambda, which is the wavelength, is also there, 6.0 times 10 to the power minus 10. And when we simplify all of these, the energy carried will be 3.3 times 10 raised to the power minus 16 joule. Okay, very simple. Now let's proceed to the next example. Here it says an electron makes a transition from minus 3.4 electron volt level to minus 13.6 electron volt energy level. Calculate one, the value of the loss of energy due to transition in joules. 2, the frequency of the emitted radiation. Taking 1 electron volt to be 1.6 times 10 raised to power minus 19 joule, and then our h, which is Planck constant, to be 6.6 times 10 raised to power minus 34 jouleseconds. Very simple as well. We write out our parameters. Now, the energy level 1 of the electron happens to be E1, and that is minus 3.4 electron volts. And then the energy level 2 of the electron after transiting is minus 13.6 electron volt. Now we have to calculate the loss of energy, and loss of energy is this symbol, delta E, which is known as delta E, or change in energy. So it's the unknown there, that's the Roman figure 1. Then we have to also to calculate the frequency, it's also unknown. Then we are given 1 electron volt to be converted. If you want to convert electron volt to joule, this is the conversion equation, and then the Planck constant. Okay, so going for the first question, the value of the loss of energy, that's our delta E. Delta E is equal to E1 minus E2. Our E1 is of course minus 3.4, and our E2 is minus 13.6. So going by this formula, so minus 3.4 electron volt minus 13.6, because the E2 is also having a negative value. So this minus is for this minus here, while the other minus belongs to the energy level 2. All right, and in our mathematics, minus times minus with plus. So going forward, we have minus 3.4 electron volt, that's this one here. Then this 2 minus become plus here, and then we have 13.6. And then when we simplify this, 3.4 plus 13.6 will give us 10.2 electron volt. And converting electron volt to joule, we multiply it by the conversion equation. That 1 electron volt equals to this. So we multiply 10.2 electron volt by 1.6 times 10 to the power minus 19. When we do that here, we'll be having our loss of energy to be 1.63 times 10 to the power minus 18 joules. Why in electron volt it is 10.2 electron volts. Okay, so we need to convert it to joule because we have been given the conversion formula. And the second question says we should determine the frequency of the emitted radiation. The frequency by formula will be loss of energy over Planck constant, and then loss of energy I've determined in our Roman figure 1 to be 1.63. So we just include that here over the Planck constant, which is the given value, so to be 6.6 times 10 to the power 34. So when you simplify all of these, we have our frequency to be 2.5 times 10 raised to the power 15 Hertz. Okay, so we move on to the next example, example 4. It says an atom radiates 1.5 times 10 to the power minus 19 joule when an electron jumps from one level to another. What is the wavelength of the emitted radiation? Given that Planck constant is 6.6 times 10 to the power minus 34 joule seconds, and the speed of light in vacuum is 3.0 times 10 to the power 8 meter per second. So sometimes you are given this, most times you are given this value, to be used. Some other time you may be asked to record them yourself. Okay, now what are we given? Right now our parameters, we are given the energy radiated to be this. So our capital E is 1.5 times 10 to the power minus 19 joule. We are also given, we are given the Planck constant to be h, which is in the bracket there. We are given the speed of light, which is c. The speed of light is represented with small letter c. But we are made to determine the wavelength. The wavelength is our lambda, so the lambda is unknown. So by formula, to determine the lambda, which is our wavelength, lambda equals the product of Planck constant and speed of light over the energy radiated. Planck constant is 6.6 times 10 to the power minus 34 multiplied by our speed of light, which is 3.0 times 10 to the power 8, or divided by the energy radiated, that is 1.5 times 10 to the power minus 19. When we simplify all of these, we have our wavelength to be 1.32 times 10 raised to the power minus 6 meters. Good, interesting, right? So we move on to the last example for today, and that is a photon of wavelength lambda naught is emitted when an electron in an atom makes a transition from a level of energy 2ek to that of energy ek. So if the electron transits from 4/3 ek to ek level, determine the wavelength of the photon that will be emitted. Very simple question as well. So one at a time, let's write our parameters. So we are given a wavelength that has this symbol of lambda naught, but we are not given the value. But then we are told that this wavelength was This wavelength was used by this photon to emit an electron, okay, from one energy level to the other. So change in energy level, that's our E naught now, would be the initial energy level, which is our 2ek, minus the final energy level, which is our ek now. Okay, that's for this wavelength, now that was used. But in the other situation now, we are told that if this electron now transit again from one energy level to another energy level again, now what will now be the wavelength? So we are looking for the new wavelength when there's a transition from one energy level to another. So we have a new energy level now. So definitely we will have a new change in energy level too. So the first one was change in energy level E naught to be 2ek minus ek, which is giving us ek, of course. Ek means 1 ek. So 2 ek minus 1 ek will give us 1 ek, or simply written as ek. And on the other hand, we have another situation in the second sentence. So our change energy level, that's our E1 now, will be the initial energy level minus the final energy level. So 4 over 3 ek minus ek this time around, that will give us 1 over 3 ek. So now we have to determine the wavelength in this situation. So we are not even given the wavelength in the first case, and we have to determine the wavelength in the second case. All right, by formula, we are going to use this formula. The product of the initial wavelength and the initial change in energy level equals the product of the final wavelength and the final initial the final change in energy level. All right, so since we are looking for lambda 1, okay, remember that we've gotten our change energy level E naught to be ek, and our change energy level E1 to be 1 over 3 ek. So when we come here, we substitute this value. Now we know that delta E naught, this one, is already ek, so we replace delta E naught with ek, and we also know that delta E1, this one here, is already 1 over 3 ek, so we substitute it also for delta E1, so we have 1 over 3 ek here. So this is our new equation. Delta E naught being replaced by ek, delta E1 being replaced by 1 over 3 ek. And when you divide both sides by ek in this second stage, we have lambda naught to be lambda 1 over 3, right? And when we cross multiply these, our result will be 3 lambda naught equals lambda 1. So the wavelength of E1 will be 3 times the initial wavelength. All right, thank you for listening. This is where we shall draw the curtain. Bye for now.